Hello, this is Simon. I'll be reviewing the bubble sort C code assembly, pipeline design, and documentation. So starting off with our C code, standard bubble sort, I included type defs to make this portable, so I don't need any included libraries. But this is the same as was given, so I won't cover this too much. But I'll go into the assembly instead more. So I use my Mac to compile with Clang for ARM7 v7a with this optimization flag for our compiler. And this reduced the instruction count by quite a substantial amount, so it would lead to easier debug later on. But that means we'd have to implement a bit more complicated ARM instructions. And this has been slightly modified from the original assembly that was given just to fit our pipeline. But just to review this a little bit, the instructions that are listed here are like a typical move, a branch, compare, branch equal, add, and then branches that are relative to the compare instruction, which I will detail in the pipeline a lot more. And there are loads, stores, conditional stores, like this example. And some additions we had to make are to add adds that would be relative to our stores. I'll explain this later on. And this is our instruction set that's here. The registers that are used and the descriptions, and some notes that we took for when we designed our Verilog. Okay, so I'll go into the documentation we have in our GitHub. Just an overview of our design goals based off of my research into ARM architecture. So we had to implement these instructions, so data processing, single data transfer, and branches. And we use these condition codes, bit 26 and 27, to differentiate between these three and a no-op, which would be 1-1. And this is the subset of conditional execution that we had to implement using the CSPR or the NZCV flags. So these are the flags listed here, and based on our assembly dump, these are the branches and other instructions that reference these conditional execution codes here. So we'd have to implement the every single of the flags and CCV, and just follow along the logic that is given here. So pipeline I will describe after this. And this is just the format of instructions, the bit fields, and what they mean for our reference. So we had to implement move, add, compare. And a lot of these are just kind of static bit fields. Compare was a bit more complicated because it updates the NZCV flags. For branching, these are the 4 instructions we had to implement, with an offset being the address here to jump to, and the condition that gets inserted at the beginning. For single data transfer, we are addressing by word, which is one of the notes that we took. So the indexing is a bit specific to our design. We would index incrementally byte 1 instead of byte 4, which would be byte addressable for a 32-bit system. It would increase from 4 to 8 to C. But in our case, we have it 0, 1 to 2. So for single data transfer, we just have a simple load and a store that is conditional, so store less than, which uses the compare as shown here. So compare always precedes the conditional execution or a branch, and updates the NCZV flags. And just a no-op. Okay, for the sake of time, I'll just continue onto the pipeline. So our pipeline, 5 stages: instruction, fetch, decode, execute, memory access, and write back, the standard MIPS pipeline similar to that. So we have instruction memory on the left and DMEM. They have write and read address for IMEM, just read data for our pipeline, and also insert instructions for processing the IMEM. And DMEM has write data, read data, and enables, and the addresses to index into. We have a PC, and the program counter increments by 1 because we are indexing by 1 instead of by 4, since we are addressing by word. This is our stage register, and that decomposes the instruction from the IMEM into the bit fields referenced by our ARM architecture that we used. So we access the reg file using rs. Some other bit fields are taken out, like the immediate I flag, S flag, and the destination register, which gets passed along the whole pipeline. And in this decode section is our condition engine. I'll try to zoom in. So this takes the condition, the first, the most significant 4 bits, and the instruction type that we kind of defined to be a branch, data processing, data transfer, or no op. So our condition engine uses the condition bit field, and it knows that equal is all zeros, and it has this static assignment based on the ARM datasheet. And it takes in the NCZV registers, which are found here at the bottom, the CSPR, which are just single bit registers that get updated if the S bit is set in a compare instruction. So a compare instruction would go through into the ALU, do a subtraction. It would not write back. It would not update any register in the reg file. It would just update these flags here. And they're based on the different conditions. So like if subtracting those two operands would give you 0, this would be 0 would be 1. V is for overflow, N is for negative, C is for carry out. So our condition engine, going back to that, would also accept or input NCCV and reference the ARM spec to produce a pass or a fail. So like if the two operands are equal, this would be the code. It would read this condition code and reference the logic as described as before in our doc in this sheet here. So Z would be set. You have to make sure of that using just the Z. And if that is true, then it'll give a pass, and that would allow for that instruction to execute along the pipeline. Else it would stop at the decode stage and bubbles would be inserted further along. So it also determines the kind of logic control that gets inserted into the pipeline relative to that instruction, so it'll stay alongside that instruction. Our ALU just has to implement add and subtract and compare, or compare does the subtract. So not too much going on there. And also updating the NCCV flags. So those are the outputs. Going into DMEM, we have write data as an input, and the address to select to go into DMEM and to select the read data to come out from DMEM. Or if there is no DMEM access, that would be skipped. If it's just a register operation, it would go through and disable writes to DMEM. And towards the end, after that, we have a write back, which is the same location as a reg file. Yeah, I think that's about it.